Someday in the future, this plane could be the new Air Force One, shuttling the President of the United States around the Earth at hypersonic speeds. If you're anything like me, you are probably skeptical of that statement. Back in 2021, I got a phone call from Hermeus, the company claiming they were going to make this a reality. A passenger plane capable of flying at Mach 5, 2.5 times faster than the Concorde ever flew. To say I was skeptical would be an understatement, but then they released this video. Hello, is that a working turbo ramjet engine? You have my attention. So I reached back out to Hermeus to take a behind-the-scenes look at what they're building, and honestly, I was blown away by a company that any aeronautical engineer would dream to work for. What I saw and heard changed me from a skeptic to an optimistic fan of the company. A company that, according to their CEO, AJ Piblica, started with humble beginnings.
Can you tell me what those early days were like when it was just the four of you in the basement of I don't know if you were literally in a basement.
We were literally in my basement with our two dogs. It was really exciting. So when we left our relatively good paying jobs and decided to jump off a cliff and try to build an airplane together on the way down, we basically kind of gave ourselves and our family 6 months to figure it out, essentially starting from nothing. Can this idea that we've got become a thing? Can we put together a plan that can get us to high-speed passenger travel in some reasonable period of time, reasonable 10-ish? Can we bring really strong people in to support that plan? Can we bring capital to support that plan? Can we bring customers? All of those questions we had to answer within 6 months.
Saying you are going to build a hypersonic plane is easy. Actually doing it is a completely different story. Software startups have a massive advantage in that they don't actually have to build anything. You can bootstrap a software startup with just a few talented and passionate founders in a garage. Hardware startups don't have it as easy, and it's why I didn't take Hermeus overly seriously until I saw they were actually building. Pretty renders of futuristic planes are a dime a dozen. Here are some we created. Designing a hypersonic passenger plane on your computer is one thing, but to actually start prototyping it requires money. A lot of money. Raw materials, manufacturing machinery, and the factory space to house them are all costs that software startups do not have to contend with. And not to mention, there is a major short supply of talented design engineers, with major competition between prestigious hardware companies like SpaceX, NASA, and Apple. Hardware startups are famously difficult to build. One of the first challenges is to demonstrate to investors that you have a clear path to revenue, and for that, you need customers. The path to selling planes in the commercial aviation industry is extremely tightly regulated. Even established multi-billion-dollar companies like Boeing have tried to skirt around certification steps when introducing new engines because it's so time-consuming and expensive. Even government-backed ventures like the Concorde, which had a max speed of Mach 2, are no longer around. Even military-backed planes like the SR-71 and XB-70 with max speeds of just over Mach 3 are also no longer operational. Trying to go from nothing to a commercial hypersonic passenger plane with a max speed of Mach 5 with no intermediate revenue is going to require some extremely patient and wealthy investors. However, Hermeus' founders, when they were conceiving the company in that basement, were well aware of this treacherous path to revenue.
We knew from the very beginning, we couldn't just raise billions of dollars to go build a really fast passenger airplane. We knew that, just like SpaceX, all the steps of technology, de-risking, and development along the way, we needed to solve important problems for customers. So it took us a while to sort out, okay, those problems are in the national security space, and they are very, very important. And that was eventually the thing that I think really got us to the first round of funding, is kind of making that breakthrough of yes, there's this long commercial roadmap, to fly passengers across the Atlantic Ocean, but the way you get there is by solving national security challenges.
So, Hermeus plans to solve problems in the national security space and generate revenue there first. So what are those national security concerns? One of Hermeus' leading investors is the US Air Force, and hypersonic technologies are a hot-button topic in the defense industry right now.
What were your most surprising findings on the threat environment, particularly with regard to China?
They're moving so fast. I think it's surprised us all. There's one other thing we should bear in mind, and that is that the things that they're producing are very technical, very high quality. They're ahead of us, for example, in some of the space issues and with regard to some of these very, very fast hypersonic type weapons.
The United States government is keenly aware that they need to catch up to maintain that terrifying prospect of mutually assured destruction, as hypersonic weapons can evade detection until it's too late to react. Intercontinental ballistic missiles are designed to exit Earth's atmosphere, travel extremely quickly at speeds of up to 7.8 kilometers per second through space, and then suddenly dive on their targets. They move quickly, but their lofted trajectory gives their enemies more time to detect and aim anti-missile defenses. Hypersonic missiles are designed to cruise within the Earth's atmosphere at about half the speed of an ICBM. The atmosphere slows them down, but their low trajectory means they suddenly appear on the horizon, previously being hidden by the Earth's curve, giving their targets minimal time to detect and intercept them. This is the national security challenge Hermeus can help address, but not necessarily by building those weapons. One of the major challenges in developing hypersonic technologies is in testing. We visited the hypersonic wind tunnel in UTSA last year to meet with Dr. Chris Combs to make a U-Haul go hypersonic just for the laugh. And while we were there, we asked about his perspective on Hermeus.
Like, one of the things I thought was interesting that their CEO said was it would be cheaper to build an airframe and make a hole in the desert than to test this in a hypersonic wind tunnel. How much truth is there to that?
So there's a broad spectrum of test, right? On the hypersonic wind tunnel side, even, there's facilities like ours where the costs are relatively low, but the scale is smaller and the flight temperatures are low. So there's certain types of facilities where you can run in for, relatively low cost, where that statement about, a wind tunnel test being more expensive than a flight scale test, that wouldn't necessarily be true. But on the other end, if you go into one of the large scale DoD production wind tunnels where you could, or at a NASA facility where you could maybe start to approach something at scale, yeah, that might be the case. You might be looking at hundreds of thousands of dollars to $1 million a day or a week to test, which, it kind of depends on how you set things up. A cheap sounding rocket test would probably be about $10 million. And so we're not talking about a flight test, we're still talking about scale. So it really depends on how big is the thing you're trying to test. Are you trying to test the actual vehicle or not? What type of wind tunnel conditions do you need? There's a bunch of variables there, but at the end of the day, if you wanted to do a full-scale vehicle, fully integrated, there's not a facility in the world where you can actually do that on the ground, so flight test does become your only option.
And that's the first market Hermeus is planning to attack: real-world flight testing. That's what Hermeus' first aircraft, Quarterhorse, will provide. It will be a reusable hypersonic testbed, providing flight testing services for companies seeking to validate hypersonic designs. It will be an autonomous hypersonic aircraft that will not just provide Hermeus with valuable lessons in developing a hypersonic vehicle, but also provide them their first revenue source, competing with the likes of those $10 million sounding rockets, while being able to provide much more data, as rockets can only fly through the desired flight regime for a very short time as they ascend through the atmosphere. This is a valuable market, with deep-pocketed clients like the US Air Force, NASA, and even SpaceX, helping bridge that revenue gap to their final goal of a commercial passenger aircraft and gaining the confidence of investors. In April 2021, Hermeus received a $60 million jointly funded contract from the US Air Force, and in March 2022, they secured $100 million of Series B funding with OpenAI founder Sam Altman as the lead investor. With this money, they have been busy working on the next critical step in developing a hypersonic plane: the engine. Boom, the commercial supersonic aircraft startup, suffered a massive setback when Rolls-Royce decided that the commercial supersonic market was no longer a priority and pulled out as an engine manufacturer, and have since had to scramble to develop their own engine, the Boom Symphony. Hermeus wisely skipped the step of relying on a third party to solve their engine needs. Their first goal with that early seed money was to develop their own subscale turbo ramjet engine. Skylar Schufert, Hermeus' chief operating officer, gave me a tour of their very first engine.
So this was our humble beginnings. So the first engine subscale demonstrator that we made. And so just to take a step back, our engine architecture is a jet engine at low speed, just an off-the-shelf jet engine, which is this section here. And then we wrap the high-speed bits around it. So everything from here back is all custom, mostly 3D printed, but could have been traditionally manufactured as well. So this is our shared Afterburner ramjet combustor. And then up front, we have our pre-cooler, obviously ground scale hardware, pretty battleship, rugged scale hardware. But the pre-cooler is what allows the jet engine to get up to the point where the ramjet can then take over.
Okay, let's pause there for 1 second, because I want this video to be as accessible as possible for people who aren't experts in ramjets or pre-coolers or afterburners or whatever the hell battleship rugged scale hardware means. By that, Skylar means the prototype engines, which aren't intended to fly, are not built with low weight in mind. They are rugged and reliable. They use cheaper off-the-shelf components where possible. They are technology demonstrators, intended for rapid iteration. Spending a lot of time optimizing for weight and other characteristics doesn't make sense this early in the process. So, if they can use a cheaper actuator designed for a battleship instead of spending an extra few $1,000s on a specialized actuator intended for something like an SR-71, they will. Next, what even are ramjets? To understand that, we first need to understand what causes normal jet engines to have a physical speed limit. Jet engines need to compress air before it enters the combustion chamber in order to extract as much energy as possible from the fuel. A normal jet engine does this with the compressor section, where air enters the engine and is squeezed down into a smaller volume by the compressor blades. The compressor is driven by the turbines, which extract some of the energy released in the combustion chamber to drive the compression stage. This type of engine has a speed limit because of all of those moving, rotating parts. As the speed of the aircraft increases, the incoming air is compressed more and more as it's forced down the inlet of the engine, which results in ever-increasing temperatures, which can eventually exceed the material limits of the compressor and turbine blades. Ramjets get around this by using the forward motion of the plane to ram air directly into the combustion chamber, so we don't need any of the compressors or turbines at all. The forward motion of the plane provides enough compression alone. However, it's not quite that easy. The plane needs to be traveling fast enough to achieve the necessary compression for combustion. A pure ramjet needs some other method to get up to speed, like being dropped from another aircraft. However, we can create a hybrid engine, a turbo ramjet engine, the same kind of engine the SR-71 used. It used a conventional jet engine with an afterburner, which is simply an additional fuel injector at the outlet of the turbine to provide additional thrust, basically an air-breathing rocket nozzle. It used this to get up to speed, and then once going fast enough, air was channeled around the compressor and turbine section and dumped directly into the afterburner and began operating as a ramjet. This is similar to what Hermeus has built, and there have been plenty of problems to solve along the way. Making the transition between turbojet and ramjet engine is not easy. It's not an instant switch. Several things need to happen as the engine transitions from turbojet to ramjet, and in that time, the aircraft is going to be rapidly decelerating as drag acts on the supersonic aircraft. If this transition isn't fast enough, the plane could end up not having enough speed to light up the ramjet. Or, for a passenger plane, the sudden deceleration could just be jarring. A lot of first-time flyers find the sinking feeling of an airliner decreasing thrust after takeoff a little disconcerting. Imagine that, but on steroids. To ease the transition, we need to push the turbojet to its limit, getting as fast as possible before mode switching. To help with this, Hermeus have installed a pre-cooler, something the SR-71 did not have. This cools the incoming air and allows the turbojet engine to operate at much faster velocities before the blades reach their max operating temperature. An engine created by the Japanese Space and Astronautical Science Institute used a liquid hydrogen pre-cooler placed in the inlet of the jet engine, in front of the air intake spike. The liquid hydrogen then travels through the inlet nozzle and combustion chamber, where it absorbs heat and turns into high-pressure gas. This high-pressure hydrogen is then injected into the combustion chamber as a fuel source. The details of Hermeus' pre-cooler are secret, but they are using a pre-cooler to push their off-the-shelf jet engine to extremes.
So that's what we did here. So we took an off-the-shelf jet engine, designed to about Mach 0.8. Used our pre-cooler, we pushed it up to about Mach 3.3 conditions, so around where the SR-71 flew in terms of temperatures. So it was about 800 F air coming in. We cooled it down to about 150 F. The jet engine had no problem. And then all of this hardware, our Afterburner combustor, was running during that whole operation. And then we pulled this out and connected the ramjet combustor directly to the facility and started it at about Mach 2.8.
What do you mean by the facility?
So to be able to test the temperatures and the flow rates associated with high-speed flight, you could do it a couple of different ways. So there's full tip-to-tail free jet testing where all of the flow is coming in at high Mach conditions. But for us, because everything internally is all subsonic, we can do direct connect. So it's not flowing high speed around, it's just kind of flowing directly into the engine. We did that testing up at Purdue University, and they were able to provide the high temperature air associated with high-speed flight, so we could prove
Is it
out
just high
all the
temperature? Is it high velocity as well?
So like I said, everything after the normal shock is all subsonic, so it doesn't have to be high speed.
Okay. Yeah.
Now, it does create a little bit of risk because you're decoupling the supersonic inlet from the subsonic flow path, but that's how we were able to do it. So we did all of this with a team of 8 people in 9 months for $1.5 million.
Wow.
Yes, you heard that right. They've developed a functional turbo ramjet engine with just $1.5 million. But of course, this is just a subscale model. It isn't intended for flight. It's a proof of concept. But they haven't stopped there. Once this concept was proven, they moved on to developing Chimera, the engine that will be used in Quarterhorse. We took a quick drive from Hermeus' factory over to their test facility at a local airport, where I witnessed a test of Chimera.
Ready. Throttle to 50. Throttling to 50.
Now, if you can't tell by the big, stupid grin on my face, I was having a great time. It felt like the entire test building was trying to take off. This was a test of their in-house Afterburner, which will be used as the ramjet after transition. After the debrief, Skylar gave me a tour of the modified General Electric J85 engine, the same engine used in the Northrop F5.
But yeah, so as with, talking down the other subscale engine, but we have the J85 core, the turbo machinery core right here. And then everything from this spot back is all of our custom hardware. So obviously these valves are battleship valves. They're not gonna be something that we fly. It's gonna be a lot bigger, but really focusing on the core pieces here that we need to test on the ground. And so that's what this configuration is. So everything is currently, the designs are being flight weighted. But even this we're using as a test bed and iterating a lot on. So the hardware that's inside of here went in like 2 weeks ago. And so that's what the team has been working on, is expanding of some design modifications for life, for endurance, for performance. And so we can use this as a test bench to just rapidly turn through things, 3D print some stuff, traditionally manufacture some stuff, and then get the performance and duration out of this set of hardware.
With these valves, they're inlet valves, or what are they?
Yeah, so these valves are to represent some of the pressure differential blow-off that we're gonna need when we do the 2-mode operation.
They're kind of bypass.
Exactly, so when we transition from turbojet to ramjet, there's gonna be a set of valves that move some of the internal systems around via pressure, and this is the ground representation of those.
Is there a pump involved with that too? Because obviously you're getting the ram air for the normal bypass air. How do you simulate that with a static test?
Yeah, so that's why some of this is blanked off, and so we just get as close as we can.
Okay. So you're just kind of relying on the the air from this kind of dragging it in.
Yeah, so you still have all the compressor powering, doing all the work against the air to
Gotcha.
kind of like pull it in.
And like you're testing the nozzle as well. Do you think that's what your nozzle geometry will look like too? Just like
Oh, definitely not that big. It'll obviously have to be a lot smaller.
right, but like just the 2 ramps. Are you just going with 2 ramp, or is it going to be more of a circular?
Yeah,
I forget the iris type thing.
Yeah, so we will. Yeah, the flight vehicle, the high-speed tail will have a 2D inlet. But when we're flying with the off-the-shelf turbojet, the off-the-shelf J85, which is some of the earlier flight vehicles, we'll just use the stock Afterburner, and that has a axisymmetric nozzle.
Back in the factory, I asked Skylar why they chose the J85 engine.
So these are out of production, the J85s. So we didn't work with GE at all. So it was all just us working with, we were really working with the maintenance, repair, and overhaul shops for them. So that's really where the expertise and knowledge lies. And these are, these engines were, I think, originally designed in like the 50s. So there's not a lot of electronics on board. There's no firmware we have to, work through. And really it's a pretty elegant, but hydromechanical system for all the controls. So really is about understanding the configuration of it, and you can kind of chase down all the different tubes and everything to understand how it works. And then there's a suite of documentation out there. So it was really on us to kind of learn how it worked.
I would have assumed you were working pretty closely with the engine manufacturers, since I imagine it would be pretty valuable for them too to have.
We certainly will be with Pratt & Whitney on the F100 scale engine, because that has digital control. It's a much higher performing engine, so we'll need to understand the details of that a lot better. And so that one we certainly will be, but this one has been around for a long time. There's a lot of people who understand this engine, and the performance needs out of it are a lot less than what we're gonna need for the future vehicles. We'll talk about Quarterhorse and the kind of scale of that, but this will power Quarterhorse, and then over here is the F100, the Pratt & Whitney F100, and that will power Dark Horse. So the vehicle that comes after Quarterhorse.
How many, is it just one engine?
2 engines.
2 engines?
2 engines on Dark Horse. And it'll be various engines on Quarterhorse depending on the test that we're doing. But yeah, so it gives you a sense of scale. So this puts out, about 5,000 pounds. This puts out about 30,000 pounds.
So it seems Hermeus are well on their way with the development of their ramjet engines, with both the J85 and much larger F100 versions being actively worked on. So what's next for Hermeus? Well, they just tested Quarterhorse Mark 0, the ground vehicle we saw being constructed in the factory. This vehicle was intended to help Hermeus develop their in-house manufacturing techniques. A lot has changed since the days of the SR-71, and this has unlocked many manufacturing techniques that the engineers of the 1960s could only have dreamed of, like large format 3D printing.
So we're also investigating large format additive. So that was like very fine, very precise. But with large format additive, you can deposit a lot more material, and so you can build larger structures a lot faster. So you can see the resolution's a bit worse, but you can put down a lot of material and build large structures. So
There's no real grain on the has that been processed to like polish?
so it's like a weld process. So you have like pretty consistent like material properties throughout.
Okay.
And so that's what we're like looking to quantify and get very.
What material is that?
This is Inconel as well.
It's so much heavier than I was expecting. Like
Yeah,
it is
yeah.
just steel.
Yeah, it's just
but
steel.
like-
It's high nickel steel.
It's just one of those things, like you read about it constantly, but I've never actually held it. And in
Yeah.
my head, I was thinking it would be closer to titanium.
Yeah.
But yeah, no, it's just heavy.
It's heavy. It's kind of like less exciting too when you're like actually looking at it. It's like,
I mean, I'm just nerdy about this sort of stuff. This,
Yeah.
this is where I get properly just excited.
Yeah.
Material science, I just think it's so cool. There's some voids in there.
So this is like a very large weld process. So
Right.
wire comes in, big laser, and
It's
you
a
can deposit a
wire
lot of,
thing,
yeah. And so that's what's actually in here. You can kind of see the robot arm that prints it. I'll take that. So it's not active right now, but you can kind of see the laser
That's
arm.
cool.
At this point in the tour, extremely loud, high-pitched grinding started, which is a common theme on these documentary shoots, so I'm going to save your ears and explain the rest in voiceover here. Hermeus have been manufacturing much of Quarterhorse Mark 0 in-house using a mixture of small and large format 3D printing and an absolutely massive CNC machine. However, One of the most exciting manufacturing techniques that Hermeus mentioned was with Machina Labs' new AI-driven robots, a robotic panel forming process that could form the outer skin panels of the planes. This technology could drastically decrease the cost of development. Body panels in automotive and aviation industries are frequently manufactured by huge hydraulic presses that force sheet metal into a mold. These molds are expensive to make, and making small adjustments to a design often require making an entirely new mold. This is also even more difficult with high-temperature alloys like titanium and Inconel, something the engineers of the SR-71 seriously struggled with. The US didn't even have hydraulic presses with enough pressure to form the panels. The best forge in the United States at that time could only produce 20% of the pressure needed to form these titanium parts. Clarence L. Johnson, the manager of Skunk Works at that time, pleaded for the development of an adequate forging press, which he stated would need to be a 250,000-ton metal forming press. Because of these inadequacies in forming capabilities, the final forging dimensions were nowhere near the design dimensions, and much of the forming process had to be completed through machining, meaning most of the material was cut away to form the part, resulting in 90% of the material going to waste. When your raw material is extremely difficult to refine, like titanium, these kind of wastes really hurt. This also makes design iteration extremely difficult. But Machina Labs are already forming titanium and Inconel parts. This, to me, is a key enabling technology. But, of course, even the most advanced manufacturing techniques don't solve all of Hermeus' technological challenges, which is why Hermeus have limited themselves to Mach 5, the lower end of the hypersonic flight regime.
And like you'd mentioned earlier that like Mach 5, there was a specific reason why you're aiming for Mach 5. Like, what is the advantage there?
Yeah, so we do get the like hypersonic bump because most people say Mach 5 is where hypersonic takes over. But it's not really about the buzzword, although that does help sometimes get people excited or make them very skeptical sometimes too. But it's really about that is where the technology cliff is. So on the engine side, it's where you can use ramjets rather than scramjets. About Mach 5.5 is where you have to go to scram because your performance losses caused by the normal shock become too much to have net thrust going forward. And then on the materials side, the temperatures that the gross acreage sit at are in a place where metallics can still.
What does that mean, gross acreage?
Yeah, the primary structure. So the primary structure of about Mach 5 sits at 800 or 900 degrees versus like the 1900 degree leading edge.
Right, okay.
And so that means that we can use metallics for the primary structure versus like ceramics that are still kind of in the development phase or like the early researchy phase.
Right.
So we want stuff that can be produced at scale and is relatively available. And so that is kind of the cliff. And so we're really at the very, very low end of hypersonic. You know, when people see hypersonic, they're like, oh, you know, it could be up to Mach 25. It's like, no, okay, we're barely hypersonic.
Right. So you're just going bare metal for the actual skin of the
There
plane.
is going to be some like judicious use of ceramics that we'll probably use in places that you might imagine, but for most of it, we can stick with, you know, off-the-shelf metallics.
And what's the reusability like there? Is like Inconel's fine for going through those thermal cycles?
I mean, it's definitely going to be a challenge. And so that's part of the work is to be very incremental about that. And our first vehicles are not going to have much life at all. And really, it's about accessing these flight conditions and starting to test at these conditions. And then the later vehicles will start to solve it. But really, you almost have to re-educate people around the life of the vehicles because like most airliners or even, you know, aircraft, the way that they think about life is like time under wing. You know, hours of engine operation, hours of flight. That is a horrible metric for us because you're not in the air that long. It's really about cycles. It's thermal cycles that are going to drive the life of these vehicles. And to be honest, we just need more data to be able to really anchor the long-term maintenance, repair, and overhaul models for these things.
Could you see yourself using, would ablatives even work at Mach 5 if you needed it?
I mean, it's definitely possible. It definitely works, But for the long-term vision that we have of being aircraft-like operations, because they are aircraft, you have to use things that don't ablate, or else you're having to replace them every time.
I mean, like the X-15 had a lot of issues with like the ablative just sticking to windows and things.
So that was when they started really pushing the flight condition up to Mach, like 6.5 towards 7. For the first vehicles, they just had straight raw Inconel on the outside. So, and that thing, I think, they flew 199 times with half a dozen or so vehicles. So that was highly reusable for like the first time they were even starting to get to these conditions with a human-rated craft. Rocket-based, so a little bit different, but yeah, just kind of an interesting
Have
point
you
for the
started,
slower speed.
like what's the biggest problems you've solved there so far? Like have you had the opportunity to test the actual airframe and see what sort of issues you're gonna have with that?
Not yet. So I mean, that's part of the work to be done. But there's a slew of other risks and problems that we have to solve. So the engine one was where we wanted to focus. You can't fly an aircraft without an engine.
Right.
So that was where we started and has spent basically, all of the time in the company up until this point. And now we're like at a place where, the major technical risk has happened or has been de-risked in terms of the mode transition. And now we're like onto the airframe side. So even just like high-speed takeoff and landing of a remote piloted vehicle is a challenge. Both of those are solved simultaneously.
What's the challenge with
So the challenge is for a hypersonic vehicle, you want to have very short, stubby wings because you don't want to take all that drag into high speed. That's really, really bad for takeoff and landing. So you're having to thread 3 needles to be able to have a vehicle that can traverse all of these flight conditions. Takeoff and landing is one where you want really big wings and you want to go very slow. For us, not able to do that. And so by adding the speed component, now the control system has to be tighter, all solvable, but not something that we have done as an organization. So that's what we're kind of focusing Mark 1 on, so our first variant of Quarterhorse. Mark 2 will be around pushing the jet engine up in flight to the mode transition point. So making sure the right flow is being fed to the engine, making sure our pre-cooler works in the actual environment. And then the third Mark will be the mode transition capable, high-speed break and airspeed record vehicle. And so being, incremental about that. So we're not going to really start to understand the thermal considerations in flight until Mark 2. But we're going to be doing ground testing along the way to be able to understand that, where we're heating up sections of the airframe, making sure that the joints and everything move the way we expect them to under load and under temperature.
Assuming each mark of the Quarterhorse is a success, Hermeus will be moving on to build their second vehicle, Dark Horse, which will be a fully reusable uncrewed vehicle designed for defense and national security missions. It will be Hermeus's primary defense product, likely serving a similar role that the SR-71 did before it, avoiding interception with incredible speed and high altitude flight. Then, finally, we've Halcyon, the hypersonic passenger plane. It bears some similarities to the XB-70 with its folding wingtips, which could actuate downward for supersonic flight. This, in combination with the triangular wedge air inlet, increased the amount of compression lift the plane could generate. Compression lift occurs as a result of extremely high pressure air created underneath an aircraft as a result of shockwave formation. Shockwaves are basically just areas of extremely high pressure after all. The triangular lip of the XB-70 air intake creates shockwaves that travel underneath the wings. The folding wingtips were positioned to reflect the shockwave back underneath the wings to increase compression lift further. This increase in lift helped increase the range of the XB-70, which was designed as a deep penetration nuclear strategic bomber. The lowering of the wingtips also shifts the center of pressure forward, which helps counteract a phenomenon where the center of pressure moves backwards in supersonic flight that can create flight instabilities. No crewed aircraft has used compression lift since the XB-70, so it's quite cool to see Halcyon taking advantage of this phenomenon. It could potentially fly passengers from New York to Paris in just an hour and a half, practically commuting distance for whoever can afford it, which Hermeus claims could unlock $4 trillion of GDP for economies with access to the technology.
Yeah, so looking back in history when we've seen accelerations of transportation networks, like when Rome built out their roads, we switched from sail power to steam power in marine shipping, or when China built out high-speed rail in the 20th century, all of those were accompanied by like multiple single-digit point GDP growth of the affected region. And the kind of reasoning behind it is when you reduce the barriers to goods moving around and people moving around, you increase trade, and that increases GDP. So there's plenty of math and stuff behind it, but it's happened in the past, and we have kind of normalized to the speed at which the world moves around. So that's what I mean by this untapped resource that we have. So and I think the pandemic taught us quite a bit about how much face-to-face really matters, especially when, like, in the early days of bringing complex goods into fruition and getting them into a marketplace. Like if you're, selling a commodity, do you need to be in person to sell coffee or refrigerator? No. A nuclear reactor, a hypersonic airplane, something like that? Yeah, probably.
How important do you think accessibility to the technology is in order to achieve that goal? And how accessible do you see, like, very far down the line of like a normal person flying on something like this?
Yeah, so to the kind of math that we've done and the markets that we've looked at is focused on business class and first class travel only, because I think that's the realistic entry point to the market. Now, I mean, we've had 7 or 8 generations of subsonic passenger aircraft now, and we're incredibly efficient at them and still continuing to get more efficient, prices coming down, safety improving, of course. Is the first generation of high-speed airplanes going to do that? No, it's going to take time to get through that. But I do think it will be very, very difficult to operate a service like this at a price point where like an economy and a premium economy ticket makes sense with the technology set that we're pursuing today. I do think there are additional technology sets that are less mature, either broadly or in an aviation context specifically, that can really kind of rewrite the rules of the test there and take that step. But it's not something that I want to sign up to do in the first generation or two. So I think the approach here is very much like a kind of a Tesla master plan, focus on the premium product, if you want to call it that, get that right, and then drive either efficiency into the system, or as a decade's worth of technology development has happened in either energy storage or energy production. I think that's the key technology area that actually enables that flip to operating cost points that make this widely accessible.
AJ mentioned energy production and energy storage being 2 key technologies that could make their technology more accessible. And that's because one of the largest costs associated with a flight is the cost of fuel. Ignoring profit margins on a $100 ticket, we can break down where your money goes to cover the costs of an airline. On average, about $19 to $21 goes to fuel, fluctuating with fuel prices. For a hypersonic plane, that fuel cost is going to be much higher, as drag increases with the square of the velocity, although that will be mitigated somewhat by much lower air densities at a cruising altitude 3 times higher than a typical airliner. Regardless, these aren't going to be cheap tickets, and that's going to be compounded by Halcyon's relatively small internal volume and the increased cost of maintenance for a plane dealing with extreme aerodynamic heating each and every flight. The reality is, Hermeus won't be selling these planes to commercial airlines anytime soon. Perhaps one day we will see a hypersonic Air Force One, allowing the President of the United States to appear first on the scene when it matters most, a powerful diplomatic tool. I often judge companies by the people working within them, and it's hard not to get invested in the vision of these companies when people like Tonio Martinez are leading it, Hermeus' VP of production. Tonio is among the most experienced engineers in the world in his field, having worked on the X-51 Wave Rider, the SpaceX Crew Dragon, and Divergent's 3D printed supercar. Experience he is bringing to developing the machine that builds the machine, where he is focusing much of his effort on ensuring everyone in the company is communicating and learning from each other.
Not a lot of engineers get the opportunity to work with both the engineering process and the actual manufacturing process. So what is that like, developing that?
That's a good question, because a lot of companies are much more siloed, where engineering and manufacturing oftentimes aren't even in the same building. And so that was a very important part of establishing this company, was having engineering and manufacturing in the same building. And what that allows for is the engineers, as they're designing their parts, they can come out and work with the technicians who will be putting things together and say, what about this, what about that? You know, make sure that the things can actually be assembled. And the same thing with the machine shop. A design engineer has to get a part made. They can go out and talk to the machinist who's going to make their part, and get pointers on, like, use this cutter and make it that radius and these types of things that the engineer may not just intuitively know, but they can get that information from the technicians to make their designs that much better to begin with. And then when the parts get made and they're actually integrating the parts onto the vehicle, you'll see the engineers and the technicians working side by side to integrate those parts and put them in. And so the engineer gets the opportunity to go through that process of, I designed this thing and this is what I was thinking when I designed it, in terms of how this thing could go together and ease of installation and those kinds of things. And then when they actually see that process or participate in that process, then they get to, oh, you know what? If I had done this a little bit different, it would have been a little bit easier. And so you get to go through those iterations at a company like this, where a lot of other companies, you just don't get that kind of opportunity.
So like that's the most, I've had a little bit of experience with that. I worked in a biomedical device startup, and very humbling experience going to the machine shop for the first time. They're like, this radius is not possible. Like, yeah, but it was the most fun part of it, of seeing even tolerancing. Like, you learn about tolerancing, but you never fully understand it until you see two parts not going together properly.
Precisely, and that's been, I think part of what's enjoyable to me is seeing the look on the engineer's face and the technicians' faces and the machinists' faces as they're collaborating and working together, and they're actually putting the parts on, and either it's like frustration or like, you know, yeah, we did it, joy. But to see that happening, especially with some of the newer engineers that are just starting to go through this process, is pretty awesome, because you can feel the level of intensity and energy increasing within the team, and the cohesion. And just we need this fast pace of iteration within the team and within all the processes that we build in order to reach our super challenging objectives.
Funny, I think like most engineers actually crave that environment as well. Like, most engineers become pretty discontent when they're pigeonholed too much into, it's ultimately a creative field. I think engineers are just like mathematically inclined artists, so they like to be like thrown into the thick of it.
Yes, and that is absolutely correct. I think some companies have so structured their environment that the engineer really gets pretty boxed in by boundary conditions, by constraints, by their environment, to where sometimes you can go up to an engineer in a big company and say, what vehicle is that for? And they may not even know, because it's just like so pigeonholed into a specific thing. Here we really encourage critical thinking across the entire team. So if a machinist is making a part, they should have a good idea of what this thing is for and what it's going to do. If the technicians are installing stuff on the aircraft and working with the engineers, we should see the interaction between these two different disciplines doing the critical thinking thing, because they get to, right? Because you actually get to do that critical thinking, and you get to make decisions based on that critical thinking. Because again, we are pushing the decision-making to the extreme. And by doing that, we eliminate a lot of bottlenecks for decision-making, as well as really making sure that the decisions are being made with in the hands of those who are actually most qualified to make those decisions, which is usually at the front line. And so all of our processes are structured around enabling the engineer and the machinist and the technician to work together to find solutions, and then just execute without any overly constrained or heavy oversight on that process.
Now, I know for a fact that any engineer listening to that conversation has their heart pumping a little bit faster. So many companies pigeonhole their engineers into ever-increasing specialization, to the point that it's hard to see the forest for the trees, and you kind of just stop learning and evolving. Every ambitious engineer wants to work in a company like this, where your creativity is not only enabled, but encouraged. And in a company with people as experienced as Tony or Martinez, you are going to learn a lot. I realized the opportunity I had to connect enthusiastic young engineers to companies like this last year. Helion told us, after our documentary with them last year, they actually hired a specialized nuclear engineer because of our video. I feel incredibly proud that our work can serve both our audience and help develop new technologies, and I want to take that to the next level. So, to help even more, I'm launching our latest project, Propeller. Propeller is our new engineering hub, where you can find the coolest jobs currently hiring in engineering. Hermeus currently has 40 job roles open, and they are looking for a lead manufacturing engineer, a principal thermal engineer, a principal structural engineer, a senior mechanisms engineer, and many more. Relativity Space, who are a rocket company that launched their Terran 1 3D printed rocket last year, currently has 171 roles to fill, with roles like Senior Director of Quality, Senior Aerothermal Engineer, Propulsion Test Engineer, Senior Manager of Test Fluid Systems, and many more. Go to startpropeller.com and take a look. If you don't see anything suitable right now, make sure to sign up to our newsletter. This is just the start of Propeller, and we will be adding many new features and jobs to the site over time. If you sign up to the newsletter, we will keep you posted on all the most exciting opportunities and news in engineering. If you are a company that's interested in advertising your jobs with us, reach out to us with the contact page on startpropeller.com.